Okay, so this will be the second lecture out of chapter 2. So in this chapter, we'll look at this concept of atomic mass units and average atomic mass. So this would be periodic table entry for carbon. So again, if you remember, the upper right-hand corner is the atomic number. That's the number of protons. And the number at the bottom is the atomic mass. So we'll see it can have units of atomic mass units, or in the next chapter we'll see that it can have units of grams per mole as well. Okay, so atomic mass units. So this is defined in terms of the carbon-12 atom. So carbon-12 atom is the standard, and it's assigned a value of exactly 12 atomic mass units. And so then everything else is compared to carbon. So if something had a mass of 1 atomic mass unit, then it would have a mass equal to 1/12 the mass of a carbon-12 atom, right? Okay, so if you notice in the periodic table entry for carbon, however, the mass is shown as 12.011 atomic mass units, right? It's not 12. Why isn't it exactly 12? We just said that carbon is defined as having a mass of exactly 12 atomic mass units. So more specifically, we said carbon-12 is defined as having a mass of exactly 12 atomic mass units. But carbon comes as more than one isotope in nature. It comes as carbon-12, carbon-13, and carbon-14. And there's 98.93% carbon-12 in nature. There's 1.07% of carbon-13 in nature, and there's trace amounts of carbon-14 in nature. And so what's on the periodic table is the average mass of all of those. And of course they have different mass, right? Because this has 1 more neutron than carbon-12 has, and this has 2 more neutrons than carbon-12 has, and neutrons have mass. So these are isotopes of each other, right? Because they only differ in the number of neutrons. And so the one with more neutrons is going to have a higher mass. So the average mass, what's on the periodic table, represents all of those. So maybe you've heard of carbon-14 before. So where have you heard of carbon-14 before? If you had, maybe you've heard of C14 dating, or simply carbon. Carbon dating, how does that work? So photosynthesis. So if we have a plant, so we have sunlight coming in from the sun, and so what are the basic components of sunlight? And you have water coming in this case it's a tree, and then what's the other major component of photosynthesis? Would be CO2, right? Carbon dioxide. And so some of the CO2 coming in, most of it has a carbon-12 atom in it. Some of the CO2 being uptaken by the plant has a carbon-13 in it. 1.07% of the CO2 in nature would have a carbon-13 in it, and then some of it has a carbon-14 in it as well, but only trace amounts. But it's instruments are nowadays sensitive enough that, sorry, that's not CO4, CO2. Instruments are nowadays sensitive enough that you can measure trace amounts of these things. So the plant is constantly taking in carbon, C12, C13, and C14, and doing photosynthesis. So then what eventually happens to the plant? So eventually the plant dies, right? Or it's eaten by an animal, and in which case it dies as well. Now then the animal is taking up carbon as well. So animals are constantly eating plant life, so animals are constantly taking up carbon as well. And so this point being is, so there's a constant ratio of carbon-12, carbon-13, and carbon-14 in nature. And so as long as the organism is alive and taking in carbon, then the ratio of carbon-12 to carbon-13 to carbon-14 in the organism remains constant. But when it dies, that is no longer true because carbon-14 is radioactive. So carbon-14 will decompose into something else, but carbon-12 and carbon-13 will not. And so then you can simply, and if you know how long it takes carbon-14 to decompose, which this is known, then you can simply compare the amount of carbon-12, carbon-13, and carbon-14 in nature And versus if this is a fossil, then how much carbon-14 is left in that fossil. And if you know how long it takes carbon-14 to decompose, then you can figure out how old that organism is, how old that fossil is. So you can use that for dating of fossils. Okay, so how is the average atomic mass of something determined? And how do you determine how many different isotopes an element has? How do you know that there's 3 isotopes of carbon in nature? How do you know there's only 1 isotope of fluorine in nature? So to do that, nowadays you can use an instrument called a mass spectrometer, so you can do mass spectrometry. So we'll go through how basically a mass spectrometer works. And so we'll use neon gas as an example. So in this case, we're going to talk about what's called an electron impact mass spectrometer. So this is basically the schematic I have drawn is basically what's inside the box. So we're going to take our neon gas sample from nature. It's a gas, so we're going to draw it up into a syringe, and then you inject it onto the spectrometer. And so it initially goes into what's called an ionization chamber. And so what you do now is you bombard it with very high energy electrons. So you've injected it into your spectrometer, it's in an ionization chamber, and now you hit it with very high energy electrons. And basically high enough energy electrons that you can knock an electron off of neon. So if you knock an electron off of neon, then what's its charge now? It was neutral to begin with because it had 10 protons and 10 electrons. But now you knocked an electron off, so now it has 10 protons and only 9 electrons, so now it's got a +1 charge, right? And so what you do is you apply a series of electric fields. And the purpose of this, since neon is charged, if you take something charged and put it in an electric field, then you can use that to accelerate it. So now you get the neon moving really, really fast in the instrument. So the neon's going really fast through the instrument, and now what you do is you push it through a magnet. So the N and the S represents the north and south pole of a magnet. So you apply a magnetic field, and what basically the purpose of that is to deflect. So it's going straight, and you put it through a magnet, and that will deflect its path. So that will make its path curve. And so you have walls on the spectrometer, and at the end of this path you have a tiny slit, and if the neon transverses the right path, then it can make its way through that slit and hit a detector. And then the detector will just count how many particles are hitting the detector in a specific amount of time. So how does this work? Because all moving charges have electric fields, and all electric fields have a magnetic field associated with them. So many of you will probably take physics 2 at some point. If you take physics 2, you study electricity and magnetism. So there you will see that electric fields, everything with an electric field has a magnetic field associated with it. So this neon plus ion that's moving through your instrument has an electric field, and therefore it has a magnetic field as well. So it has its own magnetic properties. So what happens if you take a magnet and put it in the presence of another magnet, then they'll either attract each other or they'll repel each other, right? And so that attraction and repulsion is used to bend the path of the particle. Okay, so then basically using equations from physics, so inertia, where an object in motion tends to stay in motion unless a force acts upon it. In this case, the force is the magnetic field, which is going to change its path. But you know the electric field that's being applied, you know the magnetic field that's being applied, you know the path that the particle has to transverse in order to hit the detector. And so basically using all of that and these equations of inertia from physics, you can calculate the mass of the particle hitting the detector. So then what's done is you plot this spectra. So on the vertical axis you have the intensity, which is basically how many particles are hitting the detector in a certain amount of time, and on the horizontal axis you plot what's known as the mass to charge ratio. So if the charge is +1, then you're dividing by 1, so what you're plotting on the horizontal axis is mass, right? So if you do this for neon, you get 3 different peaks, 3 different signals. So you get a signal at 19.9992 atomic mass units, you get a signal at 20.994 atomic mass units, and one at 21.991 atomic mass units. So why do you get 3 different signals? This was just a sample of neon that you put on the instrument. Why do you get 3 different signals or 3 different peaks? Because there are 3 isotopes of neon in nature. And they each have different mass, and the mass spectrometer can separate them out. And we'll explain in just a minute how it can separate them out. Okay, so cheap mass spectrometer cost about $20,000. And you can get mass spectrometers that cost up to $500,000. We have some $20,000 mass spectrometers in the chemistry department. We have a mass spectrometer that costs about $400,000 as well. So it's a cheap mass spectrometer is like a pretty nice car, right? In terms of cost. So where do you get money to buy instruments that cost this much money? You write proposals to funding agencies like the National Science Foundation, and if you get your grant funded, then you can buy an instrument. So one aspect of the cost, so why the difference in cost, would be to how many decimal places the instrument can measure your mass to. So if you want to measure it to 4 decimal places, then that instrument's going to cost you a lot of money, right? If you only want to measure your mass to 1 decimal place, then that's going to be a little bit cheaper mass spectrometer. Okay, so now how do you use this data? So the fact that there's 3 peaks tells you there's 3 isotopes. But now how do you know? Well, so let me ask you. So this first peak is neon 20. So this has 10 protons, 10 neutrons, 10 electrons, right? And then the next peak is neon 21, which has 10 protons, 11 neutrons, 10 electrons. And then the next peak, of course, would be even higher mass because it's got more neutrons. It's got 10 protons, 12 neutrons, and 10 electrons. So that third peak is neon 22. So which one is there more of, if you had to guess? Well, since the vertical axis is intensity, there's more neon 20s hitting the detector than 21s and 22s, so there must be more neon 21. And then the next most abundant would be neon 22, and the least abundant would be neon 21. You can just see that from the intensity of the peaks. But now if we want to calculate how much of each one there is, then we need to do a little bit more work. So you're not going to have to do this. The instrument does all of this for you. So if you wanted to know how much of each one there is, then what you would do is, for example, is you would tell the instrument to let's cut that peak for neon 20 there and measure the area. So we'll call that A1 for the area 1. And then tell the instrument to cut this peak here, and we'll call it and measure the area, so that's area 2. And then cut this peak here and measure the area, and then that's area 3. So now how do you get the relative amount of each one? So that's what's called fractional abundance. So what you would do for neon 20, for example, is you would take area 1 and divide it by the total area. Area 1 plus area 2 plus area 3, and if you did that, then you would calculate this number, 0.9051. And then if you did the same thing for neon 21, you would take area 2, since that's the area under the peak from neon 21, and divide it by the total area, and that gives you 0.0027. And then tell the computer to take the area for this neon 22 peak, measure the area, and so that's area 3, and divide it by the total, and that gives you 0.0922. So if you multiply these by 100%, right, then there's 9.22% neon 22 in nature. If you multiply this by 100%, then there's 90.51% neon 20 in nature, and if you multiply that by 100%, there's 0.27% neon 21 in nature, right? Okay, so now how do we use these numbers to get average atomic mass? So I just put this in a table form. So we take so this comes from the instrument, right? The instrument tells you the mass of all of these things that's hitting the detector. And the fractional abundance comes from doing this math, measuring the area underneath these peaks, and then getting their ratios. And so now what we're going to do is we're going to multiply. We're going to take this times that. So 19.9992 times 0.0951 equals this, 18.10127592. Don't round in your calculator if you're doing this. Don't round into the very end, right? And then take the 20.994, the mass times its abundance, and that gives you 0.0566838. And then take 21.991 times 0.0922, and that gives you 20.02757002. And then you're going to add these up, and that gives you this number, right? Or in equation form, it looks like this. We take the mass times the abundance of neon 20, the mass times the abundance of neon 21, the mass times the abundance of neon 22, and calculate that out, and you get 20.187. So that is the average. Didn't spell it right. Let's see if I can spell. So that's the average atomic mass of neon. So what do you do with this number? That's the number that goes on the periodic table. So the entry that I've given here, this is, so we have a periodic table that we always use, and our periodic table says 20.1797 for neon. So depending on which periodic table you look at, the average atomic mass is slightly different. So we calculated 20.187, our periodic table says 20.1797, but that's pretty close to being the same, right? That's about the 3 decimal points. If we took this and rounded it, then that would be 20.18. Well, so it differs at about the 3rd decimal point. And so, you know, different periodic tables have slightly different average atomic masses for elements, and depending on where you find the sample at in nature, natural abundances or fractional abundances are pretty constant in nature, but they're very small variations depending on where the sample is acquired from. Okay, so back to this mass spectrometer. So how can the mass spectrometer, how can it separate the different masses out? So neon 20, neon 21, neon 22 have different masses, right? How can the instrument separate those out so that each one hits the detector? So I like to use this analogy. So let's say we had an 18-wheeler, a NASCAR race car, and a remote control car, and we get them going all the same speed, and then put them through a corner, right? And let's assume that they can all maintain their traction and not flip over. So they can all make the corner, right? Well, but they cannot necessarily all hit the detector. So if you get them all going the same speed, and let's say the NASCAR is going to make its way around the corner and hit the detector, right? So if you were driving the 18-wheeler, what would you expect your path to look like? So you're going the same speed as the NASCAR, but your 18-wheeler is a lot more mass, right? So what's going to happen to the 18-wheeler? Its path would look like, it would go like that and it would crash into the wall. So it's not going to curve as much, right? Because it's got more forward momentum. And the remote control car does not have much mass, so it's going to have its path curve too much, and it's going to slam into the wall. So if you were driving the 18-wheeler and you wanted to round the corner and hit the detector, what would you do? Is you would slow down, right? So how could you slow it down? If this was a particle, so if this was a neon 20 cation, for example, how would you slow it down? Well, you change the electric field, because the electric field is what you use to accelerate it. So that would be one option, right? To make the 18-wheeler hit the detector, you could decrease its speed. You could do that by decreasing the electric field. Or the other way would be to increase the magnetic field to make its path deflect more. So you could either, something that's really heavy, you could either slow it down, and that way it has a chance to get around the corner, or you could increase the magnetic field and deflect it more. And something that's really light, like the remote control car, right? If you wanted the remote control car to make the corner, then since it's really light, you could give it more forward momentum, so you could increase the electric field to get it going faster into the corner. Or the other thing you could do is you could decrease the magnetic field so it's not deflected as much, right? But they all had to transverse the same path in order to hit the detector. So basically now you know the electric field that's being applied, you know the path that the particle has to hit, transverse to hit the detector, and that's fixed. And you know the magnetic field that you apply. So using some equations from physics, you can calculate the mass. You can make everything hit the detector by slowing it up or speeding it down or changing the magnetic field, right? And you can calculate the mass of the thing that's hitting the detector because of that. Okay, so let's just apply some of this. So lithium is found as 2 isotopes in nature. If you look at the periodic table for entry for lithium, it looks like this. So there's some lithium-6 in nature, and there's some lithium-7 in nature. So which one is there more of? So just look at the average atomic mass. Which one do you think there's more of? Well, 6.9 is a lot closer to 7.0 than it is to 6.0, so there must be more lithium-7 in nature, right? And there is. Do I have that in my notes? Yes. Lithium-7 is 92.41% in nature, and lithium-6 is only 7.59% in nature, right? Chlorine's found as 2 isotopes in nature. So in this case, I didn't give you the atomic mass of the 2 isotopes. So which do you think there is more of in nature, chlorine-35 or chlorine-37? We'll look at the average atomic mass. That's 35.4527. If it was about a 50-50 mixture, you would expect that number to be about 36, right? About halfway between the two masses. It's closer to 35 than it is to 37, so there's more of this in nature. So chlorine-35, it's about 75.78% chlorine-35 in nature, and 24.22% chlorine-37 in nature. Bromine's also found as 2 isotopes in nature. So in this case, I've given you the atomic masses for the 2 isotopes, and if you notice the average atomic mass, it's about 80, so it's about halfway in between, but it's a little bit closer to 79 than 81. So it's about a 50-50 mixture, but a little bit more bromine 79 than bromine 81. So there's 50.69% of bromine 79 and 49.31% bromine 81, right? So you can look at the average atomic mass and figure out, without doing any work at all, which one is more abundant in nature. Okay, so back to this neon example right quick. So what if I gave you the average atomic mass, but I didn't tell you how much of one of the isotopes there was? Then you can solve for this, right? So how much neon-22 is there in nature? Well, you just call that X and solve for X, right? Or maybe I didn't tell you what the average atomic mass of neon-22 was in nature. So maybe I told you what this was, but I didn't tell you what that was. So then you would just call this X and solve for X, right? Okay, so carbon-12 is defined as having a mass of exactly 12 atomic mass units. So carbon-12 has 6 protons, 6 electrons, 6 neutrons. So if carbon-12 has a mass of exactly 12 atomic mass units, why doesn't neon-20 have a mass of exactly 20 atomic mass units, right? The 6 protons, and most of the mass of the atom is coming from protons and neutrons, right? Because they're about 2,000 times as massive as electrons. So electrons don't contribute much to the mass of an atom. So if 6 protons and 6 neutrons is 12, then neon-20 with 10 protons and 10 neutrons, why isn't it 20? So it's a question a student asked me once in lecture, and at the time I didn't know the answer. I'd never noticed it before, never thought about it before. So I was in a jam, so I had to go look it up. I had to go think about it, and then when I looked up the answer, then it was obvious to me. It's like, can't believe I didn't think about that. Well, so the reason why is because of this. E equals mc squared. Maybe you've seen that equation before. So E is Einstein equation, right? E is energy, m is mass, and c is the speed of light. So for all nuclei, so carbon is 12 because AMU is defined in terms of carbon-12. 6 protons, 6 neutrons, 6 electrons is defined as exactly a mass of 12 atomic mass units. And then everything else is relative to carbon. But the point is, sum of the mass of an atom Some of the mass of an atom is tied up as energy. It's what's called the nuclear binding energy. It's basically what helps keep that nucleus together, because it's a really small space, right, with a lot of positives, protons in a small confined area. So what keeps that nucleus together is what's called the nuclear binding energy. Some of the mass of the atom then is converted to energy. And so all atoms weigh less than they should, because some of the mass of the protons and the neutrons in the nucleus is converted to energy to keep it all together. Okay, so just to reiterate then, that is the average atomic mass of all of the isotopes in nature. So carbon-12 has a mass of exactly 12 atomic mass units, but there's some carbon-13 in nature which has a higher mass, and some carbon-14 in nature. And if you took the mass times the abundance and then added those all together, you would get the 12.011, right? So the number at the bottom you have to keep in mind is the average atomic mass. Okay, we'll stop there.